Hey, it's me, Destin. Welcome back to Smarter Every Day. Okay, we are kicking off the Coast Guard series in full effect here. Today, we want to get to the good stuff. We're going to start learning about search and rescue. And when you think about the Coast Guard, you normally think about like an airplane, well, it's a helicopter, I'm sorry, a helicopter like this, or you think of an RBM like this, a response boat medium. These things are awesome, and they're used effectively by the Coast Guard to save lives for what's called SAR, search and rescue. But today, what I want to do is I want to focus on the search part of search and rescue, because we don't really think about that. Sometimes we think about like you got the helicopter coming over the horizon, going down, picking somebody up. We'll do that in the future, but how do they know where to go? This deep dive series into the U.S. Coast Guard is incredible because I had no idea that the Coast Guard did so many different awesome things. Today, we're going to focus on how the U.S. Coast Guard uses math and science to find people in the ocean. Let's go get smarter every day. So in our last episode on the Coast Guard, we visited Sector Mobile on the Gulf Coast of Alabama, where we saw a command center at work. We also met with Captain Allen, who's in charge of Sector Mobile, which means she's in charge of all the Coast Guard assets along a vast stretch of the Gulf Coast of the United States. I asked her about how they approach finding people who are lost. When you dispatch your air assets or boats or whatever you dispatch, do you have them search in a certain way?
We do. We have various search patterns depending on the search object. We put various search objects in there because sometimes we don't know if we're searching for a cuddy cabin boat, whether a swamped, capsized boat. They all float differently. A person in the water, a person with a life jacket, a person without a life jacket. We do various searches, and we put different assets on different patterns so that we're covering that whole area. That drift is what we call it.
Really? So a person in the water in a life jacket is going to float different than just a flat bottom boat in the water?
That's correct. Absolutely.
In what way? How would that be different?
Well, it depends on the current, surface currents, underwater currents, and then also the air. Which direction the air is.
Because the water could be flowing one way and the air could be flowing the other. What does that do?
We put it all into the SAR database, and it usually spits out a great product for us that we can base our search patterns on. It'll put out a search pattern, various search patterns, and we give those to our boats. We give them to our air assets. We give them to everyone that's searching. Okay, that was fascinating. The idea that different things float differently in the water, and the way they float determines where they could be. That's where the survivors are. That's crazy. Okay, and Captain Allen talked about this modeling and simulation software that the Coast Guard uses to find people. And in the last episode, if you were paying close attention, there was this really brief moment where there it is, right there. See it? Okay, zoom in. And enhance. Okay, so this is modeling and simulation software, so I'm using context clues here. The purple things seem to be like simulations of probable locations where something may have drifted off or something like that, and we're trying to find it, and so this black line seems like a search pattern, and this first one makes sense to me because when I color something, I start at one side and I methodically cover the entire area all the way over to the other side, make sure I didn't like miss anything. But this other thing is a little strange to me. I don't really, it's not intuitive because it's like triangles, and that doesn't seem like an efficient way to cover an area. So what's going on with that? This weird shape is a concept the Coast Guard uses called a Victor Sierra, otherwise known as a sector search. It solves a very interesting problem that occurs when you search for someone on water. Let's say you went on a hike and you lost something. The right thing to do is just go back to the last place you remember having your item, and it's probably in that general area. This works because land doesn't move. Water, however, does move, and it can even change flow directions over time. If you were to go back to the same place where you lost the thing, it's probably already drifted away on the water. Understanding that drift that Captain Allen was talking about, you remember when I did that? That drift, that's the key to finding people, because I thought that the coasties would just roll up in their boat and just start looking around, maybe use a searchlight at night or something like that. But no, they have to do two things really, really quickly. They have to first
first find the drift of the water, but they also have to start searching, and this Victor Sierra kind of does that. And the cool thing about coasties is that their training is standardized, so it doesn't matter where you go talk to a coastie, they all know how this works. So what I'd like to do is I'd like to go talk to coasties from 2 different locations and see if we can understand it. We're actually going to do a Victor Sierra down here in Florida, but first I want to go up to Station Rochester in New York on Lake Ontario. This is Bosun's Mate 2nd Class Lucas Weston. Lucas and the rest of the crew showed me the RBM, or Response Boat Medium, that they used here at the station. And once we went into the station, I got a chance to ask them about what a Victor Sierra is.
So what we're doing for a Victor Sierra, a sector search, is we are trying to look for a small search object in a very well-known location.
Okay.
What you're doing with those triangles is you're covering a small area a lot. So as you're searching, you're actually moving with the current or the wind. So you figure out how fast the water's moving, whether it's by wind or by current, and then the direction it's moving. The thought process behind it is if someone's fallen overboard, they're not going to drift against the wind or against the current. So you want to follow the direction that they started to drift in.
If you don't speak Coast Guard, it might be difficult to understand what he was saying, so let's just go do one. Let's go down to Station Destin in Destin, Florida, and let's learn how to do a Victor Sierra search pattern. Obviously, I think Station Destin is really cool because my name is Destin, but the cool thing about this particular trip is I went on Memorial Day weekend, which is the busiest weekend of the year for this station. There's this little makeshift island that pops up just offshore from Station Destin called Crab Island. It's where a bunch of people go party and all kinds of stuff. It was a really interesting time to visit. At one point, while hanging out in the cafeteria and just getting to know some of the coasties, I learned one of the most important things that the Coast Guard taught me.
All right, so this is Justin, and he's going to teach me how to whistle, because you whistle at the college kids, right?
Yeah, so you're gonna put your hands together, 2 guns, pinky should line up,
Finger guns, all right?
fingers together,
Yeah?
and all you do is you just push your tongue back and blow down.
What do you mean? Oh, this is... Hold on, wait, what did you do with your tongue? Let me see it.
So you push it back
Uh-huh,
and fold it over,
uh-huh.
and you just blow.
All right. All right, you got that one. Finger guns, like that?
Yep.
Knuckles together.
So your pinkies, you see these 2 lines right here?
Yeah.
Line those up.
Okay, got it.
Okay, and then fingers together, and you want to fold your tongue over,
Uh-huh.
and then blow down.
Holy cow! Are you serious? Dude!
And then once you get that down, you can do it with one hand, the same way, just folding your...
Are you serious? Justin, thank you so much.
You're welcome.
That was a moment, dude.
Yeah.
Okay, obviously that was awesome. Anyway, the next day before Crab Island started to form, I got to go see them prep one of the boats for the day. This is an RBM, Response Boat Medium. It's a 45-foot long jet boat, and this is one of the workhorses of the Coast Guard. Ortiz and Machachi showed me some of the secrets of the boat as they were getting things ready, and it's awesome. I got to go out with them later and do some of their drills with Shepard and LaBeouf. That's Justin, who taught me how to whistle. They took the RBM several miles off the coast out into the deep water to do some training, and this is where I started to understand that nuclear sign we saw on the SARUP software.
All right, let's do Victor Sierra.
Do a what?
So it's a search pattern. It's a drifting search pattern. So we use this if, say, we someone says, we get a radio call, hey Coast Guard, I'm in this position, there's a person in the water, and we fly out there and we get on scene and we don't see anybody. We're gonna do what's called a sector search, or a Victor Sierra search pattern, and you'll see more of it when we run through it, but basically that drifts with the current.
You gonna draw it?
Yeah, so I'll show you what a Victor Sierra looks like on paper, and then when we get done, I'll show you what it actually looks like, taking into consideration the current and the drift.
You want me to take the sticks?
Yeah, go ahead.
So you're taking control?
Taking control.
So if this is the starting position, Victor Sierra is going to be like this, and we'll end right here.
That's a Victor Sierra?
That's a Victor Sierra search pattern. So we'll start this way, and then it just goes all the way around. On paper, it looks like we're going to end up in the same spot, but you'll see on the chart plotter here in a minute, it's not going to look anything like this when we get done. our track.
How do you command the boat to do that? Are you saying I'm going to run for a certain amount of time at a certain speed?
Yeah, so we go a certain speed for a certain amount of time. So we'll run 6 knots for 1 minute.
And that'll take you how far?
0.1 miles.
Okay, got it.
When I start, I'll set a waypoint. And now there's a waypoint on our position.
Uh-huh.
You see it there?
Yeah.
Zoom way in. It's a waypoint on our position. When I finish, I'll set another waypoint. And I'll use the distance and the direction to determine set and drift. And we'll use that to plug into our precision search patterns. So, you know, get a good search area, figure out the most probable location for that search object.
So how long does a Victor Sierra take?
About 9 minutes.
Okay.
We have 9 legs, a minute apiece. The current and the winds can affect that. Maybe it'll take 9.5 minutes, maybe it'll take 8.5. But we're gonna try and turn for 6 knots. Once we get our speed set, we'll leave it. We won't touch our speed. We'll just let the current take us. So this is a search pattern wheel. And so
Oh, it's a nomograph.
it basically will tell you what courses you need to steer. So we're gonna start out at 200 degrees, and then I know my next course is gonna be 330.
So where are we? So we're in the center right now, right?
Right.
Where's the first one?
Leg 1 right here.
Why did you choose that course?
So looking at the elements coming this way, the wind coming from the north, just estimating, that's what I estimate set and drift is gonna be.
Uh-huh.
So when we come on scene, we'll just estimate, and then when we finish, we'll get the actual set and drift. But you always wanna try and go with the elements.
So you're trying to maximize the area you cover while also taking into account drift.
We're trying to cover a specific area because we know they're in that specific area.
Got it.
Okay, this is the nomograph that Justin's using for the Victor Sierra, and I love nomographs. It's a mechanical way to calculate things quickly. So let's check this out. So if you look at what he was doing, you've got this little spinny wheel here, and it has a bunch of arrows pointing in different directions. And you'll notice that the compass heading, when we were in the boat there, started at 200, which is pointing in this direction. So what this does is this tells the boat crew what compass heading they should do the first leg on. After that, they're going to do this other heading over here, which is parallel to this, and you can just simply look at the nomograph. Boom, we're going to go 320 on that next one. So you can basically go through all these, and you can use the angles associated with whichever equilateral triangle you're dealing with, and then that's a quick way to calculate your compass heading. I think these things are awesome, and it's clear there's other kind of cheat sheets here, time and scale, speed stuff. This is what Justin's using to calculate the compass headings for the Victor Sierra.
Okay, someone go to the bow and deploy datum.
Got it.
That's the datum.
Yes. You can see it. That's how it's going up. So we can see it at night.
Okay, this is so cool. I had to use this as an excuse to get one. I know the word datum from mechanical engineering to mean a place from which you can measure other things. Now, usually a datum is stationary, but this is a floating datum. And I think that's really cool because if one side's heavier than the other, you can make the orientation operate this little switch in here and light up that thing. Isn't that awesome? Anyway, so I think this is fascinating because you don't usually use the word datum for a moving thing. So the question is, how are they going to use a moving datum? By the way, this is not a satellite tracking device. It's literally just a floating light that blinks.
If we arrive on scene, possible PIW situation, first thing we're going to do is deploy datum to get the most calculated set and drift.
Datum deployed.
Yeah, so he's gonna back off of it so we're not affecting it. And then
I'm going to back off far enough to where I can pass it going 6 knots. So once I pass it going 6 knots, we're going hands off the throttle so we can maintain that same engine speed the whole time.
ROTs, you're gonna have port lookout, Machachi starboard lookout. Keep you eyes forward and I'll be all around lookout.
Roger.
We're gonna come up to 6 knots, about 1100 RPMs.
Roger. Coming up.
Pass datum on your starboard side. Your first course is gonna be 200.
200I. 1100 RPM.
Come down to...
Yep, just past 6 knots, gonna come down to 950.
So as soon as he passes it, I'm gonna drop a waypoint and we're gonna use that to determine set and drift when we're
Approaching
done.
datum, going about 7 knots. Gonna drop it down just a little bit more.
Just hold it
Datum
there.
out the right window now. Steering course 200.
200I. Next course is gonna be 320 and 50 seconds.
320I.
This is fascinating because there's so many different concepts happening here all at once. They're following a pattern that essentially breaks up a circle they're searching into equal pie pieces, which gives them the most efficient way of searching that circle for the PIW, person in the water. So there's two sides of the boat, the port and starboard. I remember port is on the left because port has 4 letters and left has 4 letters. So with Ortiz looking out the port side and Machachi looking out the starboard side and Shepard looking out the front, they're able to cover every point in the pie in a very methodical way. Now this would be pretty simple if they were on land because the land doesn't float in one direction or another at varying speeds. The center of the circle would stay in the same position in terms of where they are on the surface of the earth, which means the GPS location of that circle would stay consistent. But on the ocean with a current, the circle will need to move with the current in order to be relevant. And that's why they drop the datum in the water, to give them a way to keep the middle of the search in line with the drift of the water. And they use math to make sure that they're still cutting the moving pie pieces up equally as they search. To minimize cross drift, they set up the first leg of their search in the direction that the current's flowing as best they can tell.
So at this point we would be going over what our search object is. We're looking for a 40 whatever year old male, blue shirt.
Oh, I see. I see. I'm 39, thank you.
I wasn't describing you at first, but then I just picked blue shirt.
20 seconds. 320. Come
No.
to starboard.
Come to starboard
320.
eye. So hard to write. Coming to 320.
Are you looking at
this? Need to look at it though.
Sorry.
You're good. Alright, 320.
Alright, wanna come look?
Yep, you're good.
So you're gonna hold that.
Do you see datum off your starboard beam?
I do, straight out the starboard beam.
All right, come to starboard, start on datum.
Go to starboard, steer on datum eye. Straight off the bow.
I do not see it.
So,
Directly off the bow, 100 yards.
Oh wow.
a little bit hard to see in the sun glare.
That's hard to see.
Okay, this is something I didn't think about. If you think about the challenge of trying to find a human at about 1/10 of a mile, it doesn't seem that difficult, right? The thing is, you're not looking for an entire human body. You're only looking for the part of the human that's up above the water. And if you can think about how the Coast Guard works, you might have a human head in a life ring like this, right? So a human head at about arm's length in front of you is about a foot or so, right? That seems reasonable. But if you do the math real quick, that same human head at 1/10 of a mile or 528 feet is more like 47 thousandths of an inch. If I do this right and I go 1/10 of a mile away, that should be about as big as my head is. It is very difficult to see something out in the water. I couldn't do it at all. The Coasties were great at it. Another thing to think about, if there's water going up and down in between me and you, if it's a consistent wave, it's gonna cover the object half the time. My point is, it's very difficult to see things out in the water with your eyes.
So are you following a course or are you going
No
at the datum?
course on this leg. I'm aiming at datum.
So once you pass datum, you're gonna come to 080.
Okay, I don't know if you heard what Justin just said, but it is critical to making a Victor Sierra work. He said they go out on a compass heading, they turn on a compass heading, and then they head back towards the datum, not on a compass heading. So basically, they put this thing over the nose of the boat, and they're going straight at datum, and as soon as they pass datum, then they pick up their compass heading. This is critical to making sure that the Victor Sierra moves with the drifting water. Also, I feel like I need to confess here, I wanted to get a really sweet view from the top of the boat by clamping a GoPro up there, but sometimes I'm an idiot. I went up there to try to like turn the GoPro on, but I was out of phase and I turned the GoPro off, and I feel shame and I'm sorry.
All right, so once we finish the Victor Sierra, what we're gonna do is we're gonna measure the distance between the waypoint we dropped when we started and the waypoint we dropped when we finished, as well as get the course. So I've got 153 degrees magnetic at 50 feet. So over the course of 9 minutes, we drifted 50 feet. So now we just do the math to see how far we drift in an hour, and that's gonna be our drift, and the set is gonna be 153 degrees magnetic. 50 feet over 9 minutes, hardly any set and drift at all. It's gonna be like 0.02 knots.
So calm seas.
Yeah, it's very calm out here. We're not drifting very much. As you can see on the chart, the Victor Sierra is almost perfect.
Yeah.
So, you know, in heavier weather, you know, that Victor Sierra is gonna look like this. It's gonna come, you know, it may look something like that.
Oh, okay.
This is one of the most perfect Victor Sierras, completed Victor Sierras I've ever seen.
Really?
This is one of the calmest days I've seen out here.
Okay, check this out. Let's simulate the GPS coordinates of an RBM performing a Victor Sierra in different types of sea drift. Man, that was a sentence, wasn't it? The higher the drift rate, the more crazy the pattern looks. But if you think about it, that's actually the right thing to do because they're actually cutting the pie up with that drifting section of water. And furthermore, they're getting data that they can then feed back into the sector command so that they can input that data into the SAROP software so they have the best chance of releasing other assets that might need to come on scene to help with the search and rescue. This is fascinating. If you were to draw this and say, hey, this is what we're going to do when we get to scene, and this is the best way to find you, that is not what I would think the visualization would look like, but this is an awesome way of doing things. I think the Victor Sierra is incredibly clever, but it is applied in certain situations. There are other types of search patterns in other situations, and to learn more about those, let's go back up to Station Rochester and ask the Coasties what's up with that.
Okay, so what are the other kinds of search patterns? Because there's other ones, right?
Yes.
What you got?
So you have an expanding square, which is another form of a drifting search pattern. Kind of like the same thing, it's more for a concentrated area, but you're slowly building a bigger square.
So is it like playing the game Snake?
Yep, you're making 90-degree turns, and you're going 1 minute, and then you're making a 90-degree turn going 1 minute, making a 90-degree turn going 2 minutes, making a 90-degree turn going 2 minutes, and then 3 minutes, and so on, and you're just building a square that's bigger and bigger and bigger.
Okay, so what else do we have? We have any other kinds?
You have parallel search patterns. You have creep search patterns. So if you had a rectangle-shaped search area where you deemed this is the area we're going to search, if you were going to do a parallel, you would search long ways.
Okay.
And if you were going to do a creep, you would search short ways.
Oh, okay. So it's you're coloring the square.
Yep.
We have like a barrier search, and that would be like for a river example. Like Station Niagara does a lot of barrier searches.
Okay.
So they'll set in one spot and basically go back and forth to catch anything that's coming down the river. So there's search units further up. They're just making sure if anything gets past them, they can catch it coming down the river. And then there's track line patterns. So if we know a vessel left in a certain direction, like they had an overdue vessel, they knew they went in a certain direction, we can follow that track line and search for them along that line.
Or like people go from Florida to Bimini, whatever, they know that's a track line, just go.
Huh. Okay.
And then shoreline search would just be, we get as close to shore as we can go, and we're looking for somebody maybe on the water or a vessel or something like that. It's just kind of a quick and dirty search for us.
Victor Sierra, expanding square, parallels, creep. Then we have what was the one where you go back? Barrier. And then you have the shoreline. And then the last one was a track line. Wow. That's awesome. That's cool, though. Is it fun?
Yeah.
It can be.
Sometimes it sucks.
Yeah.
You're out there in like 8-footers and you're taking them beam too, because that's just how the search pattern is. Like, if they're drifting that way, and that's how and this is the most probable area where that's going to be, that doesn't mean it's working with the elements. So you might be going 2 miles in one direction and the waves are just hitting you beam too, and that's just how it is. There's nothing you can do about it, but that's the most probable area where they're going to be, and that's what you have to do.
Oh, wow. So the search patterns calculated at sector are often independent of what the water's actually doing. So
They try to work with us best they can, but in some situations they just can't do it.
So what do? You say, hey, sector, I'm taking big waves over here from my left.
Yeah, you can tell them that, and they'll be like, okay, like I might have a different way they can do it, and then they'll try to change it for you if they can. But if they can't, it's you got to work with it.
It's just what it is. It's interesting that the situation on the ground or in the water, so to speak, is often different than what it looks like at sector. Yeah. What was that smile?
No.
What was it? I saw the smile.
It's just two different.
Is it?
Two different areas.
It's the true, isn't it?
Two different worlds. That's all it is, but you know.
The biggest thing
We all
is
work together pretty fluid as a team to accomplish the mission when it really comes down to it.
we rely heavily on them to be that big picture person, but we're also their eyes and ears. So we see anything, hear anything, we let them know, and that helps them determine and help close out the case.
Have you ever calculated a search pattern for somebody out on a boat?
I've seen how it works, but I've never actually used the computer program, how they do it.
Did that give you a little bit of empathy towards
On why the search pattern ends up how it does? Yeah, definitely made me understand it a little more.
Do they send you the search pattern?
Yeah, so they'll send it to us in the version of waypoints. That's it. We won't see all the little, the computer program that creates all the possible
The particles.
particles and where they would go. We won't see that. We'll just get the waypoints of this is where you need to drive.
Okay.
The Coast Guard is working on now with the new SINS packages that are coming out on the new boats. They're trying to implement a way for them to send the search pattern from their office directly to us, right in front of us, so we don't have to take the time and put it in. They can say, "Here's your search pattern. It's out there," and we can just start following it.
It'll just come up on the RBM screen.
Be able to pop up and go instead of us manually entering every single waypoint. That's going to save so much time.
Sounds like we need to prioritize that in Congress. Stroke the check, make it happen. That's awesome. Thanks, guys. Appreciate it. Boom. Boom.
So obviously we can't end a video like this without pulling some dummy up onto the side of an RBM and saving them, right? Which is what we'll do in just a minute. This episode of Smarter Everyday is sponsored by Brilliant. Brilliant is a really cool app and website that lets you learn through interactive content at your own pace. In this video, the Coast Guard used probability in a software package called SAROPS to figure out where survivors might be located in the water. Now, if you're like me, it's probably been a while since you brushed up on probability. Brilliant has tons of interactive modules that'll help you understand how probability works. This is just scratching the surface of Brilliant. If you want to check this out, you can get it by going to brilliant.org/smartereveryday. That gets you a 20% discount on premium membership, but you can sign up for free and just start messing around with stuff and see what you think. If you're like me, you actually like touch things to learn. Like you want to see how the thing works, how it fits in the whatever. That's what Brilliant does, but for very complicated concepts. And when you walk away from a module, you end up owning it. Like you understand the concept. Brilliant.org/smartereveryday to sign up for free. Also, that gets you 20% off an annual premium membership. The whole point of Smarter Every Day is to get smarter every day, and Brilliant helps you do that. So big thanks to Brilliant for sponsoring Smarter Every Day. Big thanks to you for supporting the sponsor. That makes these videos happen.
Quest to bring them on board.
Bring him on board, I.
1, 2. Don't come guys neck.
This is a stressful situation. You're not supposed to laugh, Ortiz.
Sorry, I'm sorry. Just knocked him out.
Did he make it?
All right, person on board, check the CABs. Appears to be stable.
I'm not sure that he's breathing.
You're not?
Yeah, I think he's going to need mustache to mustache. Okay.